started. So I'm very happy to welcome you to the third day of the Geometry of Moduli session. And to kick it off, we have Hannah Larson, who's going to tell us about moduli spaces of curves with polynomial point counts.
All right, thanks so much. Thank you to the organizers. It's a pleasure to speak here. So the work that I want to tell you about today is all joint with Samir Canning, Sam Payne, and Thomas Willwacher. And this is about the geometry of the moduli space MG parameterizing smooth genus G curves. And in this talk, I'm going to highlight 3 invariants for studying this moduli space and how they relate to each other. And each of these invariants captures different information about the geometry of MG. So our first invariant is algebraic in nature. It's the Chow ring. This is something that captures information about all of the algebraic subvarieties of MG and how they intersect each other. Our second invariant is topological. Now we're going to think about the complex points of MG in the classical topology, and we'll look at their singular cohomology. And the last invariant is arithmetic. I'm allowed to think about MG over any field. So I might think about it over a finite field, and when I do, there's just some finite set of points, and the natural thing to do is count these up. So in the first part of the talk, I'm going to focus on this lens of point counts over finite fields. And we'll see, as the talk goes on, how these other invariants come into play. So as some motivation and a preview of some of the ideas in action, let's take a look at the example of projective space. So projective space has this nice affine stratification. And if I want to use that to count points, well, I can just count up the number of points in each of these strata and add them up. So I get q to the n plus q to the n minus 1, all the way down plus q plus 1. Now there's another way that I could count points on projective space. You could also recall that Pn is an plus 1 minus the origin mod scaling. Now in general, when we see a quotient like this, we're not allowed to just say number of points on top divided by number of points on the bottom. But that is allowed when you're quotienting by a connected linear algebraic group. So in this case, on top, we have q to the n plus 1 minus 1 for the origin points. And then I divide through by q minus 1, the number of non-zero scalars. And you'll see that you get the same answer as we did before. This affine stratification also allows you to calculate the Chow ring and the cohomology ring of projective space. And in this example, everything lines up really nicely. So the Chow and cohomology rings are isomorphic, and the point count is a polynomial, and furthermore, the coefficients that we see in front of these powers of q are the dimensions of the even cohomology groups. So, in part inspired by this example, the main question that I want to address in this talk is, when are the point counts of MG over finite fields polynomials in Q? So given its interpretation as a moduli space, here when I'm talking about point counts, I want you to think about the coarse moduli space, if you like. So this is the number of geometric isomorphism classes of smooth genus G curves defined over FQ. Now, if you want another concrete way of thinking about this point count, you could just recall that MG is a quasi-projective variety. And that's true over spec Z. So I can situate it in Pn here, where it's the vanishing of a bunch of polynomial equations, maybe minus some smaller vanishing set. And those polynomials have integer coefficients. And I've just told you about the FQ points of Pn, So you could go ahead and plug in and see which of them lie in this quasi-projective algebraic set. Let me pause to see if there are any questions about this main question. So, spoiler, this is, oh, yes. So I want you to just think about the course moduli space. So then it's like literally how many points are there? But there is also a notion of stacking point counts, where you weight by the order of the automorphism group, and it actually turns out for the Lean-Mumford stacks, the stacky point count agrees with the point count of the course moduli space. Any more questions? Yes?
What do you mean by the geometric isomorphism?
So we're looking for like when I have a curve over FQ, and it's isomorphic to another one, that isomorphism might be defined over some extension of the ground field. So I need this word geometric in front of isomorphism classes. That's what the course moduli space, its points are like these isomorphism classes over FQ bar. Yeah. Okay, so this description is absolutely not how we count points on MG. There are two ways that I know of, and one is a sort of explicit construction like we saw for projective space, and the other is using cohomology. So as an example of the first way, let's look at genus 2 curves. So a great thing in genus 2 is that every curve is hyperelliptic. So it's going to have the form y squared equals f of x for some polynomial f. And after I choose my coordinates x0 and x1 on P1, this f is going to be a member of this set of square-free homogeneous degree 6 polynomials. Now this depended on my choice of coordinates, but if I get rid of that choice of coordinates, so I quotient by this GL2, then I actually get a presentation of M2. So I find out that M2 is an open subset of affine space mod GL2. And GL2 is a connected linear algebraic group. So I'm allowed to do point count on top over the point count on bottom. And on top, you can count these square-free polynomials using a sort of inclusion-exclusion argument, and then you could count the points of GL2 over FQ using the orbit stabilizer theorem, if you like. And what you'll find is there's some cancellation in this expression, and the point count of M2 over FQ is Q cubed. I want to point out that this presentation of M2 is also exactly the sort of thing that allows you to compute its Chow ring. And more generally, people have used sort of explicit constructions of moduli spaces of curves in low genus to compute their point counts and their Chow rings. So in genus 3, for example, every curve is either hyperelliptic or a smooth plane quartic. And we can deal with each of these pieces in a similar manner to how we did on the previous slide. And that's what Mujanga and Faber did to compute these invariants. And then there's a similar story in genus 4. Again, we have a really good understanding of the canonical models of these curves. Now, while the point counts are only known up through genus 4, the Chow ring has been computed even further up to genus 9. So here, the case of genus 5 is due to Izadi, 6 to Penev and Vakil, and then 7, 8, and 9 are joint work of myself and Samir Canning. So I want to kind of compare and contrast what goes into calculating the point count versus calculating the Chow ring. So for point counts, you need a very good understanding of each of these strata. But once you count up the points in each stratum, you can just add your answers all together. For Chow rings, you might need less information to get a handle on what is the Chow ring of each strata, but the problem of piecing these back together is much more challenging because this excision sequence in Chow need not be exact. So this method of kind of explicitly writing down a stratification of your moduli space works well in low genus, but there are obstructions from birational geometry to continuing much further. Well, so it's known that the moduli space of curves is unirational in genus up to 14. So this means I can at least write down a dense open subset of the moduli space. But the moduli spaces of general type once the genus is 22 or more. And in particular, this means it's impossible to even write down a dense open subset of the moduli space. So despite this, we do have a theorem that characterizes the shape of the point counts for any G. So we've proved that the point count of mg over fq is a polynomial in Q if and only if the genus is at most 8. So in order to give you a little more context for where this cutoff between 8 and 9 comes from, and also to introduce some of the key characters in this story, I also want to address this question of when is the point count polynomial for moduli spaces of curves with marked points. So now MGN is the moduli space of smooth genus G curves with a choice of n marked points on it. So in genus 0, if we want to count points, we can use the write it down method very effectively. N03 is just a point, because I can take any 3 points to 0, 1, and infinity. Then when I go on to N04, my 4th point is just somewhere on P1 minus 3 points. And then if I want to figure out what's happening in general, I can think about this forgetful map from M0n to M0n minus 1. And the fiber of that forgetful map is just P1 minus the n minus 1 points that I already marked. So you can use that to inductively show that the point counts are given by this formula, which is a polynomial in Q. Now, the write it down method also works in genus 1 up through 10 markings. But then something interesting happens when we add in the 11th marking. So it turns out that the point count of M111 over FQ is not a polynomial in Q. And in fact, it is a polynomial minus tau of Q, where this here is the Ramanujan tau function, the qth Fourier coefficient of the weight 12 cusp form for SL2Z. And the existence of this weight 12 cusp form also allows you to see that H11 of M111 bar is non-zero. In fact, it has a holomorphic form, which basically comes from this weight 12 cusp form. And once you know that there's a holomorphic form, you know that M111 is not rational. And it also implies that the Chow groups of 0 cycles are really big. So in particular, the Chow ring has no hope of being tautological. Any questions here? So this sort of really interesting thing happens at M111. And it's going to come back again later in the talk. So in genus 2, there is work of Bergstrom and Faber, which shows that the point counts are polynomial up through 9 markings, but then not when you add the 10th. And in genus 3, it's polynomial up through 7 markings, but not when you add an 8th. I do want to point out in these genus 2 and 3 cases, this first x is now occurring in the range where the moduli space is unirational. And also when we happen to know that their Chow rings are tautological. So in general, there's really no reason for this cutoff to all line up between your different lenses. Just think about P2, right? That's nice and rational, polynomial point count. But then you go ahead and remove something that does not have polynomial point count. Now it doesn't have polynomial point count, but it still has, it's still rational, still has nice Chow groups. So given this chart, a question that was posed by Kieran Kadlaya is, what is the first n for which this point count of ngn over finite fields is not a polynomial? And our theorem is an answer to this question. So if you look at the n equals 0 axis, this is the theorem that I first stated, and it says once you get to genus 9, already with no markings, your point count is not polynomial. And then between genus 0 and 9, the formula for the first n, which is not polynomial, so the first x that you see when you look up in this chart, is ceiling of 25 minus 3g over 2. Should I think? Oh, yeah.
Is not the most polynomial. Is not the most polynomial.
It's not.
At most polynomial. It's bounded by a polynomial.
Oh, it's bounded by a polynomial. You could always find a polynomial bound. Yeah, it's not too hard to show. Yeah. Yes. Thanks. Any more questions? So let me say on here, this formula shows that the answer of when this first non-polynomial point count occurs is actually governed by a straight line in this Gn space. All right. Let me pause here again. Any more questions? Yes, please. Yeah, so a consequence of our work is going to be the question. Oh, yes, sorry. The question is, for which of these x's can we say that the difference between some polynomial and the point count is controlled by coefficients of some modular form? And a consequence of our work will be that at least the leading order correction to what the failure of this to be polynomial is controlled, in fact, by this tau of q. So that was a big spoiler for a lot of the talk. Any more questions? Yeah.
So I assume when you mean it's not polynomial, you mean like as you vary over all q?
Over all possible q, so over all prime powers.
You know something about if I fix a characteristic, I take powers to that one characteristic. There could be exceptional characteristics where it's still a polynomial, like when the tau of q is 0 simple.
So the question is, do I know anything about just fixing the characteristic and then varying powers of that prime? I don't think I have anything to say about that right now, but that's an interesting question. Any more questions? Yeah, please. That is an open question. So yeah, one thing I was going to say is that we conjecture that the rest of this chart should be filled out with red X's, but we don't know for sure. We have computationally checked that it's filled out by x's at least when g plus n is less than 150. But the rest is open. Any more questions?
What about the same question for NG and bar?
That is also a great question. Yes, we could. So the question was, what about polynomial point counts for ng and bar? And there, I forget the exact number, but there is a g after which we know it cannot be polynomial. But we do not know how to entirely fill in the chart. And for ng and bar, this question, like in some ways is easier, in some ways is harder because it's proper. So some things line up more nicely, but we also do not have a complete answer there. Yeah. Any more questions? All right, thank you for all the great questions. So in the second half of my talk, I want to tell you about what goes into proving this theorem. So one of the very important tools is the Grothendieck-Lefschetz trace formula. So this is something that relates point counts to cohomology. So this is going to be for x a smooth Deligne-Mumford stack over specs v. So its point counts are given by this formula here, this alternating sum of the trace of Frobenius acting on the étale cohomology of x over fq bar. So let's unpack this formula a little bit if you haven't seen it before. So this is just a vector space over QL. And if you like, you can picture it as this marble run. And we have an endomorphism called Frobenius. And it's going to give us a linear transformation that acts on our cohomology. And all we have to do is just take the trace. So I'm going to take the sum of all of the eigenvalues of this linear operator. So it's a theorem of Deligne that all of these eigenvalues have absolute value q to the k over 2 for some integer k. And this k is called the weight. So one possible eigenvalue that we could have would just be a power of q. So q to the I would be considered weight 2i. And these pieces of the cohomology where the eigenvalue is a power of q are called Tate type. So then I think you'll see that if all of the cohomology is Tate type, then when you take the trace, you will just be adding up a bunch of powers of q. And so you'll find that the point count over fq is just a polynomial in q. Now the converse of this needn't be true. Just because your point count is a polynomial does not imply that all cohomology is Tate type. And that's because this sum here was alternating in degrees of cohomology. So something that could happen is you could have non-Tate pieces that occur equally often in odd and even degrees, and so cancel each other out in this alternating sum. So inspired by this, I'm going to define the weight k Euler characteristic to be this alternating sum of the dimensions of the weight k pieces of the cohomology. So then lemma is that if the point count is a polynomial, then all of the odd weight Euler characteristics must vanish. Right? Think about this polynomial, right? That's a sum of even weight terms. I'm saying if there's anything odd weight, it must cancel itself out. So our goal, if we want to prove that the point counts are not polynomial, would be to show that some odd weight Euler characteristic of ngn is non-zero. So how do we compute these weight-graded Euler characteristics? So the first step is to compactify Ng inside Mgn bar. So when we do that, the boundary is stratified in a really nice way, where each piece of that stratification is the image under a gluing map from a product of smaller moduli spaces. And the thing that I need to understand in order to compute the weight k Euler characteristic is how the degree k cohomology pulls back under all of these gluing maps. Maybe also some additional information when there's symmetry introduced with these gluing maps. So if I know all these pullbacks, then I can just feed this into Deligne's weight spectral sequence, and it will compute the weight k cohomology of Mg. Now, we are interested in the case when k is odd. And so if we look at the odd degree cohomology of Mgn bar in low degrees, it turns out that it vanishes. So hk Mgn bar is 0 for k equal to 1, 3, 5 by work of Algebraic and Cornalba, and 7 and 9, more recently by Bergstrom, Faber, and Payne. And if you plug 0 into this machine, then 0 is the only thing that can come out. So if we are looking for an odd weight Euler characteristic that's non-vanishing, the first place that we have any hope of finding it is in weight 11. And we've already seen, I've mentioned that H11 M111 bar is non-zero. So that is some non-Tate type piece of our cohomology. And in fact, the trace of Frobenius on H11 M111 bar is that Ramanujan tau function. So this is the first time that we see some non-Tate type piece showing up. But what I'm going to explain to you in the rest of the talk is that this H11 M111 bar also controls everything happening in weight 11. In some sense, this is the origin of all weight 11 cohomology. Let me pause here if there are any questions about what I've said so far. Yeah. The point count of the hyperelliptic locus itself, that was the question, right? And in that will be a polynomial. And that is something that you can show using the write it down method. And it would be very similar to what I said about M2. Thank you. Can I say anything about the degree of the polynomial? Yes, the degree of the polynomial will be the dimension of the moduli space. Yes, just like we saw for Pn. Any more questions?
You know, the point count and the trigonal locus in the polynomial?
I don't know that. It's possible that it may be known, but I don't know. Oh, the question was, is the point count of the trigonal locus a polynomial? All right, so in order to explain to you sort of why this H11 M111 bar is the origin of everything that happens in weight 11, I want to tell you a bit about Arborello and Cornalba's inductive method to prove their vanishing results. So the starting point for them is this long exact sequence in compactly supported cohomology, which is associated to the open inclusion of Mgn inside Mgn bar. And the complement is the boundary. So a result, if we rewrite Harer's VCD calculation in terms of compactly supported cohomology. It tells us that the left-hand term of this sequence on this slide vanishes when 2g minus 2 plus n is greater than k. So that means that then the next map here, pull back to the boundary, is injective, at least when g and n are sufficiently large compared to k. Now, Arborel and Cornelba's insight is that we should try pulling back not just to the boundary, but to the normalization of the boundary. And this is good because the normalization of the boundary is a disjoint union of these products of smaller moduli spaces. And they proved that when 2g minus 2 plus n is greater than k, the composition with this pullback all the way to the normalization is injective. So why is this so useful? Well, let's suppose that you knew that the odd cohomology of mgn bar vanished whenever 2g minus 2 plus n is less than or equal to k. So then I claim that you would have an injection like this for all k. Because, well, when 2g minus 2 plus n is less than or equal to k, the left-hand side is just 0. And when it's greater than k, that's the injection from the previous slide. And now this is really useful for induction because let's look at this right-hand side. Remember, k is odd, so I can, when I decompose this into Kunith components, at least one of the degrees in that Kunith decomposition is also odd. And then these really are smaller moduli spaces, so I can inductively assume that their odd cohomology vanishes. So the right-hand side is 0 by induction, and if you inject into 0, you must be 0. So just from knowing the vanishing of odd cohomology in this finite region of base cases, we learn that the degree k cohomology vanishes for all g and n. So I've pictured on this slide the base cases that are needed to run Arborel and Cornelba's induction in degree 9. Now I said we want to go on to degree 11. If we want to do that, we are going to need more base cases. And also, we're going to need a way of running this argument even when one of the inputs is not vanishing. So something interesting has to happen here when I go on to degree 11. But of course, it's good that I have a non-vanishing base case because this is our non-Tate type piece that's going to allow us to see that lots of point counts are not polynomial. So where do more base cases come from? This is where Chow rings come back into the story. Now that, right, I'm looking to understand something in this finite region where g and n are small. This is where the write it down method really shines. So this is a theorem joint with Samir Canning. We prove that for every blue dot that you see in this chart, that is an instance where the Chow ring of mgn bar is equal to its tautological subring. So this is a subring that is relatively well understood. So this, you should think of this as basically completely determining the Chow ring in these cases. Now, in order to prove this result, we stratify the moduli space into lots of pieces. And when we did this, oh, I meant to also say, some of these results were previously known when the Chow ring is tautological, to the left of this line by Keel, Faber, Mumford, and Belaruski. Okay, but to advance beyond these previously known cases, we stratify the moduli space into a bunch of really nice pieces, and we observe that these pieces have a certain key property, which is called the Chow-Kunith generation property. So I'm not going to go into what that means, but this is the part of the talk where I want you to think back to projective space from the very beginning. Right? Projective space had that stratification into affine cells, and those were sort of so nice that it meant that the cycle class map was an isomorphism. So these pieces are not quite affine spaces, but there's something really nice about their cycle theory, which ensures that the cycle class map is an isomorphism. So if the cycle class map is an isomorphism, I can turn all of these blue dots into green dots, where the cohomology of MGN bar is tautological. And tautological classes always live in even degree. So in particular, I know that at every one of these green dots, all of the odd cohomology of MGN bar vanishes. And now you see we have filled up the base case region to run Algebraic and Cornalba's induction. And there is just one base case which has non-vanishing H11 at M111 bar. So we were able to improve upon Algebraic and Cornalba's inductive method to now give a complete description of H11 MGN bar for all GNN. And it turns out that H11 vanishes when the genus is 2 or more. I think this was somewhat of a surprise at first. And then in genus 1, all of H11 can be explained in the following way. Just think about your M1N bar and forget a subset of all but 11 points. Then you can pull back H11 from that copy of M111 bar. And these pullbacks generate all of H11. We also know all the relations among those pulled back classes. In fact, we know H11 M1N bar as an SN representation. So this is enough information to now plug in to Deline's weight spectral sequence. But this time we're plugging in something non-zero. And so there's some really interesting combinatorics, which was carried out by Sam Payne and Thomas Willwacher. And they obtained a generating function for the weight 11 Euler characteristic. Let me pause again for any questions so far. Oh, yeah.
Can you say a couple of words about the type of combinatorics?
The type that, like what this generating function looks like? Yes. Well, let me just go on to the next slide then and say that we were able to analyze the asymptotics of this generating function quite explicitly. We sort of know its exact growth rate. And I'm not going to be able to tell it to you off the top of my head, but we know very well how it grows. And so we were able to bound it away from 0 once the genus is larger than 600, and then we explicitly compute the remaining on a computer. Yeah, and the result that we find is that the weight 11 Euler characteristic of mg is non-vanishing, so the point count cannot be a polynomial if and only if g is at least 9 and g is not equal to 12. So in other words, there is a surprise that happens. The weight 11 Euler characteristic of M12 vanishes. And it seems that this vanishing really is accidental. So one of Thomas Willwacher's students, Pascal Skipnis, has computed the weight 11 part of the cohomology of M12, and it turns out to be non-vanishing. And what happens is that the pieces in degree 31 and 32 are equal in dimension and cancel each other out in this Euler characteristic. So what do we do when the weight 11 Euler characteristic vanishes? Doesn't really help us tell whether or not the point count is polynomial. So the answer is, you guessed it, we go on to weight 13. So we also have a complete description of H13 of NGN bar for all G and N. This is again proved using our improvements upon Algebraic and Cornalba's inductive method. And you'll realize, well, that means we also needed a lot more base cases as well. So there was really some finesse that went into getting these additional base cases. But the result is that H13 is actually generated by push forwards of H11 on boundary divisors. So these can be represented in a way sort of similar to how we represent tautological classes in cohomology. So in order to get some H11 in your boundary divisor, you need to have a genus 1 component that has at least 11 markings on it. But if you do, then you can just slap this omega decoration onto it and push forward. So this implies in particular that the only weight 13 pieces that we see in the cohomology of NGN bar and NGN are Tate twists of our H11 and 111 bar. And since we understand H13 so well, we also know sort of all of the relations among these decorated graph generators, and we know it as an SN representation. This is the sort of thing we can plug in to the weight spectral sequence and calculate the weight 13 Euler characteristic. And for M12, it's -6. And since it's non-zero, that tells us that M12 also cannot have polynomial point count. So for the other red X's in the chart where I had some positive number of markings, again, it's proved in a very similar way. We compute the weight 11 Euler characteristic. But again, there's this kind of accidental vanishing that happens in genus 8 with 1 marking. But it turns out that the weight 13 Euler characteristic is enough to show that the point count cannot be a polynomial. So in this slide, I want to summarize sort of all the tools that go into this method for proving non-polynomiality. So the first step is that we start with Chow rings and the write it down method. This leads us, by the cycle class map, to understand that there's lots of vanishing odd cohomology in these base case regions for Algebraic and Cornalba's induction. And then using their inductive method and improvements upon it, we can get a complete description of the degree K cohomology of the compactification, which in turn helps us compute the weight K cohomology of the open moduli spaces. And that is what, by the growth in Dieck-Lefschetz trace formula, can tell us about these point counts over finite fields. So this is the strategy for proving that the point counts are not polynomial. I'll just end the talk by saying one more slide about what goes into proving the point counts are polynomial. So if you think about this chart that I've used with G going horizontally and N going vertically, the sort of most natural slope of a line in this chart is -2. Because, well, we know how to glue together 2 points, and that adds 1 to the genus. So when, like, if you have some point in the moduli space, all the ones that are going to show up as factors in the sources of gluing maps for its boundary stratification, they lie on or below the line of slope -2 through that point. So if you're trying to prove polynomiality, it's sort of easy to do so if you have spaces that are all very nice in some triangle bounded by a line of slope -2. So the largest region you can make like this, where there's no non-Tate type contributions, is the region that I have highlighted here. So in these cases, sort of, it's pretty immediate from our results on Chow rings that everything in this sector must have a polynomial point count. But the line that showed up in our theorem was a line of slope -3/2. So there's a couple spaces in this orange region where maybe you know, like there's a filled blue dot here, which will imply that the point count for the compactification is polynomial, but you maybe have to subtract off something from the boundary. And these are spaces where there could be a contribution from M111 showing up in its boundary. And so the key thing that's at play for why these additional spaces in this orange sector turn out to have a polynomial point count too, is that there's some symmetry often in these gluing maps. So the simplest example of this is if you think about M2 9 bar. It has a boundary stratum. The irreducible boundary stratum is the image of M1 11 bar under a gluing map. But that gluing map factors through the S2 quotient, which exchanges the two markings you're gluing together. And this means that the sort of contributions you get from this boundary strata, the only ones that can survive are the ones that are S2 invariant. And we happen to know that H11 and 111 bar is the sign representation when you permute the marked points. So that is the end of my presentation, and thanks so much for listening.
Okay, questions for Hannah? I'll run to you.
Does the weight 13 Euler characteristic vanish somewhere where the weight 11 doesn't?
I don't know. I don't know that off the top of my head. We have some data about both of these that go pretty high, and so we might have one, but I'm not sure. But that's a good question. Yeah.
Thanks. What could be the first example of Algebraic cohomology that doesn't Larson in the
Yes. I have a bonus slide. It shows up on H15 and 115 bar. And so you should picture this as some kind of different looking non-Tate type piece. And this is associated to the weight 16 cusp form for SL2Z.